Okay, today we're going to do friction, but we're going to do it on an inclined plane. Now, I just wrote down some steps that when you're not sure what to do, if you follow these steps, it'll make it easier for you to solve these problems. So number one, you're going to draw your what's happening picture. So your what's happening picture is really your free body diagram, and it shows all the forces acting in the direction in which they act. Now, remember, when you have a force, you always have the tail coming out of the center of mass. Now, on the FRQs in AP Physics, sometimes they might have a problem, and they might ask you to draw the free body diagram, and that might be 4 out of 15 points on an FRQ. So those would be like the 4 easiest points that you could get on an FRQ because you're basically drawing like 4 arrows. But then if you don't draw it in the right direction or something like that, or you draw the components of the force, then they're going to take off points or you're not going to get credit. All right? You have to do a free body diagram because we're going to be getting to problems that are going to be much more complicated than what we did in honors physics. You can't solve these problems having a free body diagram in your head. You have to do it on paper. Remember to establish your sign convention. Now, even though a lot of times we use the standard Cartesian sign convention that up and to the right is positive, many times in this class we're going to be doing problems where, number one, we're going to change our sign convention. So if something's on an inclined plane, we're going to make our sign convention going either up or down the inclined plane. What I do is I draw my sign convention on my diagram because then it helps me to visualize, what's positive and what's negative. Then you're going to break your forces going up perpendicular and parallel to the surfaces in contact. I don't want you to memorize that you're always going to do that because in the next unit we're going to do centripetal force. And when we're doing centripetal force and we sum forces, we're going to make positive in the direction of centripetal force. So there are going to be exceptions. For example, when we're doing a car that's driving on an embankment that's at an angle, but the car is going this way, so the centripetal force acts towards the center. So we were going to make that positive. So there are going to be exceptions. So don't memorize. It's always going to be perpendicular and parallel because that's one of the things I try to trick you on the AP test. In every single problem, there's 3 things we're going to do. We're going to sum forces horizontally, we're going to sum forces vertically, and we're going to use the mu equation. Are we definitely going to do in that order? No, but when you get to it and you do it and you're like, oh, I'm missing something else, and you just do something else. When you don't know what to do, you go to the end, and then you think backwards, and that kind of helps you to sequentially solve the problem. So in this class, again, whenever you're working one of these problems, go to the end, and then think about what you need to do. So before, when we had a flat surface and the weight acted down, the normal force acted perpendicular to surfaces in contact. But on an incline, again, the normal force is going to be perpendicular, so you never want to memorize that the normal force is equal and opposite the weight, because that's not so. All right, so let's start some of the homework problems together. So let's do 12, and then we'll do 14. Oh, okay, wait, so let's do 6, and then let's do 8. Oh no, I want to do ones that are accelerating. All right, we'll do 5 and 6. How's that? All right, number 5. It says a 3-kilogram wooden box. I'm going to write my given. The mass is equal to 3 kilograms. Slides from rest, so that means that the initial velocity is 0, down a 35-degree inclined plane. How long does it take the box to reach the bottom of the 4.7-meter wood incline? So first of all, the main thing to realize with this is In order for something to move, there doesn't always have to be an applied force. There doesn't always have to be a push or a pull. So let's say this is my incline, and you can't see, but it's tilted. If I put the penny on it and I have it inclined, it's inclined about 15 degrees. Is the penny moving? No. But if this angle is great enough, the penny slides down the incline. Okay? So what happens is if the angle is great enough, the component of the weight is going to pull the object down. So you don't always have to have an applied force, and that's one of the biggest misconceptions that people make is, oh, there always has to be something pushing or pulling it, and there doesn't have to be necessarily on an incline. Okay? So the first thing we're going to do is we're going to draw our free body diagram. Okay? So over here, here's my incline, and I'm going to do a box to represent the object. And then I'm going to have my weight acting down. The object is moving down. So one of the things I like to do is just kind of show so I know which direction it's moving. Because whatever direction that it's moving, in this case, I want to make my sign convention going like that. So I'm going to make down the incline positive, and I'm going to make up positive. Oh, I also forgot in the given to write mu is equal to 0.3. So if the object is moving this way, the frictional force acts opposite the motion. And then my normal force always acts perpendicular to the surfaces in contact. So this shows all the forces acting on the object. That's my free body diagram. So if this was an FRQ, this might be 1, 2, 3 points. Okay, right there. The only thing is, in order for me to sum forces, all my forces have to go either perpendicular or parallel to the surface in contact, or they have to go according to my sign convention. So I see that F of F is going this way, F of N, F of G is not. So I'm going to take F of G and I'm going to break it up into horizontal and vertical components. Now what I like to do is I like to do it to the side. So I'm going to do it to the side here and I'm going to draw it. This is F of G. Now I'm just going to draw a little pencil on here because I don't like to mess up my diagram. But from geometry, if I want to draw my perpendicular, you can just draw imaginary like this, that going like this and like this. So there's my 90-degree angle. And if you flip this over, this angle here is similar to that angle here. And some people have a hard time visualizing that. So here's this triangle, but then if I flip it over like this, we see these are similar triangles. Okay? So here, this one, I'm going to call F of G, I'll call it perpendicular, because it's perpendicular to the surfaces, and I'll call this one F of G parallel. Or if I want, I can call this FGY and FGX, because I'm calling this kind of like X and Y, even though it's tilted. You call it whatever you want. All right, so this angle here is similar to this angle here. So this is 35 degrees and this is 35 degrees. So again, you don't want to memorize that something is sine or cosine. You have to look at your diagram. So when I look at this diagram, first of all, I want to calculate the magnitude of the weight, which is mg. So it's 3 kilograms times 9.8 meters per second squared. So F of G comes out to be 29.4 newtons. Now I want to find these components. So FGX, if I look at my picture, this is opposite that angle. So it's going to be FG sine of 35. So FGX would be 29.4 times the sine of 35. So FGX is equal to 16.9. FGY is adjacent to the given sign, which is cosine. So FGY is equal to FG cosine of 35. So it's 29.4 times the cosine of 35 degrees. So FGY is equal to 24.1. Now what I need to do is, before I start summing forces, I need to redraw this diagram showing all my forces going perpendicular and parallel to the surfaces in contact. So I'm going to redraw it. Now once I do this, the whole problem's easy, and I'm just going to do my three things. I'm going to do my mu equation, and I'm going to sum forces horizontally and vertical. So FF stays the same, Fn stays the same, and then instead of f of g, I'm going to have FGY, and I'm going to have FGX. And you have to make sure you draw these in the right direction. So that's why when you have this, when you draw your components head to tail, you know, if you draw these incorrectly, this is going to mess up your free body diagram. And again, this is my sign convention. So how do I start? Well, first of all, in this problem, they want me to find the time. And time has nothing to do with my free body diagram. I know I'm going to use my straight line motion equations. So when you don't know what to do, you go to the end. I want to find the time, but then if I look at my other givens, I have m, I have x, and I have v naught as 0. So because I know that I want to find t, and I have x, and I know v naught is 0, and I can end up finding a, I'm going to say which equation has those four variables. So that's x is equal to v naught t plus 1/2 at squared. If I rearrange that equation, t is equal to the square root of 2x over a. I have x. So obviously, once I find a, then I can go back and find the time. So when you don't know what to do, you go to the end, and then it'll tell me, oh, once I find a, I'll be able to solve this problem. All right, so where do I start? The block is not moving vertically, so I'll start summing forces vertically. So I'm going to say summation. So first I'm going to put my sign convention. Summation of f of y is equal to ma. Is this block accelerating this way? No, it's not even moving, so this is 0. So now I'm going to add up all the forces going in the y direction. So I have Fn going up, which is positive, Fgy going down, which is negative. So Fn minus Fgy is equal to 0. So F of n is equal to Fgy, which is equal to 24.1. Now I'm going to sum forces vertically. Summation of f of x is equal to ma. Is this block accelerating? Yeah, it's accelerating down because we need to find the acceleration. So now I'm going to look at my free body diagram. Remember, down is positive, this is negative. So now, instead of this, I'm going to replace this with what's in my diagram. So I see FGX is positive, minus f of f, and that's equal to ma. So a lot of times in high school physics, they'll say, oh, magic working equation. It's not magic. It comes by summing your forces. So I have FGX, and I don't have f of f, do I? But I do know that f of f is equal to mu times f of n. So now I'll rewrite this, and I'll say FGX minus mu times f of n is equal to ma. So I'll go ahead and rearrange that, and then I'll substitute in all my values. Or I can substitute them in now. So a is equal to FGX minus mu times f of n over m. So FGX was 16.9 minus mu, which is 0.3, times f of n which is 24.1, divided by the mass, which is 3 kilograms. So the acceleration comes out to be 3.2 meters per second squared. And now I'm going to go back to what I did up here, now that I found A, and I'm going to say, I know that x is equal to v naught t plus 1/2 at squared. It started from rest, so v naught is 0. I rearranged the equation to solve for the unknown in terms of the known, so now I'm going to substitute it in. T is equal to the square root of 2x over a. So it's equal to the square root of 2 times 4.75 meters divided by 3.2 meters per second squared. So t comes out to be 1.7 seconds. Step by step by step. There's no shortcuts. You can't do these problems without doing free body diagrams. So again, you start off with your given and everything else.